In this video, I'm going to be talking about the engineering systems component of the technology course for Year 8. I'm going to be talking about building and testing a model bridge. So, to start off with, I'm going to be talking about these 5 points. To start off with, I'm going to be talking about why we build bridges, why engineers build bridges, what do civil engineers do, bridge materials, bridge designs, and tips for your bridge. So first of all, why do we build bridges? Well, imagine that your school was on the other side of this valley. Now, there are situations where this is a thing, where people live on one side of a valley because there's good farmland, and on the other side is the town and the schools and the other things that people need. So every day, these people, if they want to go sell things or if they want to take their kids to school, they have to go on this zip line and use that rope to get to the other side. Now, there's many reasons why I could talk about why this would not be ideal, but we could just talk about in terms of the practical aspects. Well, you can't take a truck over a zip line. You are going to get wet if you're on a zip line. It's not particularly comfortable. It's not necessarily the fastest way to get somewhere is to sit in a harness. So that's where I guess you think about what would happen if you had to take a zip line every day to get to and from school. Whereas many people take bridges to and from school without really considering it. So what we're going to look at here is, this is the city of Sydney, and this is how long it would take for you to get to and from school. To get from Sydney to North Sydney, if you didn't have the Sydney Harbour Bridge, the tunnel, or the other bridges. That cross the harbour. If you had to cross, even where I have the crossing at Rydalmere, there's still a very small bridge that you would have to cross anyway. But the difference is that what would be I think it's a 2-minute drive. I think it's only a 10-minute walk over the bridge. Would become, I think that'd have to be well over an hour to drive that way, and without even considering the time, it uses a lot more petrol. Now, petrol is a non-renewable resource that contributes to climate change. So there's a big environmental benefit in building bridges. So we also have the case of level crossings. So where trains and cars meet, if they don't meet one doesn't pass over the other at a bridge, they meet at an area called a level crossing. So you hear the bells, the ding, 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 and then the arm comes down, and then the train passes. Now, if you've ever experienced this, you may have only waited for a minute or two, but in some situations where there are freight trains, you might find that you're waiting for well over 10 minutes as a freight train passes. And that is a very frustrating thing as a driver or even as a passenger when you're waiting 10 minutes for a freight train to pass at a level crossing. The last point I want to talk about is safety. That it's a lot safer to have, say, this pedestrian bridge than it is to have the traffic lights, because some people, particularly young people, tend not to want to wait at traffic lights, and they tend to be very poor judges of when is a good time to cross. But by having a pedestrian bridge, we have fewer. We don't need to stop the traffic, so we have a time saving, but also we have a safety benefit in that there's no way that someone can run a red light, or that a pedestrian could could cross against the red man, and as a result, we have fewer incidents, fewer accidents. Okay, so the next point I'm going to talk about is, what do civil engineers do? So there are many different kinds of engineer. So mechanical engineers build vehicles, and they also the machinery that make all the stuff that we use, like from lunchboxes to pens to the International Space Station. That they're all built by mechanical engineers. So electrical and telecommunications engineers, they support things like our phone network and the telecommunications network. So that's how we have the internet. And then there are other different kinds of engineers, like chemical engineers, biomedical engineers, environmental engineers, and probably a few others that I'm forgetting. But what we're going to focus on today is we're going to focus on the oldest kind of engineer, the civil engineer. And what do they do? Well, they focus on 4 main things. They worry about efficiency, they estimate forces, they design solutions, and they're usually managers. So what does efficiency mean? Well, in the case of engineering, efficiency means building bridges on time and under budget. So it's important that no one wants to wait forever for an engineering project. So whether or not it's your house that's being built, you don't want to no one wants to have a build their house over 4 years. They want to build the house built as quickly as possible. The same is true for bridges. No one wants to wait 20 years for a bridge to be built. They want it built in the shortest amount of time practicable. Now, they also no one wants to spend twice as much for a house. People would rather have 2 houses rather than one. So they would, or they'd rather have a bigger house if they can afford it. So no one wants to waste money on building a house. The same is true for bridges. That if we can build a bridge for half the cost, it means we can build a bridge somewhere else, or we can save the taxpayers money somewhere else. So time and budget are very important for engineers. It's also important that when we're thinking about efficiency, that we're also thinking about value, that we're making sure that we're doing the work in such a way that it's going to be easy to maintain, so that we don't end up building a bridge once and then have to rebuild it twice as often. So we want a bridge that lasts for a long time, and it's not going to cost a fortune to keep it the standard that we need. So that's where we talk about efficiency. The next thing is about load calculations or force calculations. And so for people who design bridges, most of the time that they spend at universities learning how to estimate what sort of forces are likely to be on a bridge, and then to design a suitable well, actually, we're going to cover that next. So a big part of what we do is learning what is a realistic expectation of what are the forces that are going to be on our bridges. And then once we know that, we're going to design a good solution. So on the left of this slide, I have the original sketches, the pre-World War I sketches of of the proposals for the Harbour Bridge. Now you can see that none of those bridges look like our modern harbour, the actual realised Sydney Harbour Bridge, and that was because the bridge was delayed because of World War I, and the bridge ended up over time another design became more feasible, and that was the design that was chosen. So design is a field in itself, but something we do before we do the design is we do something called a structural analysis, which is where we consider the forces that are from our design, and using that estimation of loads, we figure out which parts of the bridge are going to be most likely to fail, which parts of the bridge need additional support, and then that goes into our design. So we use, based on our understanding of our estimate of the forces, our knowledge of the materials, and our knowledge of the geometry or the shape of the bridge, we can use all of those things together to come up with a design. Once we come up with a design, engineers will produce a proposal document. And the proposal document will say to whoever's paying for the bridge, so that's usually, say, like the state government or a state authority, so like the Roads and Maritime Authority, for instance, they will be in charge of approving the work. And they'll a bridge will a document will be put to the government, and the government will take it to various people, members of the public, and even the newspapers will probably look at it, and based on that, they will make the decision whether or not to go ahead with the work. So that's all part of what happens in design. And then once we've had the proposal be approved, that engineers will then design in detail how the bridge is going to be built, and then someone will manage the construction of the bridge. And then after the bridge is built, there'll be someone else who manages the operation of the bridge and the maintenance of the bridge. So what do managers consider? Well, they consider safety, they consider cost. So cost is the money, and how much it costs to pay for people to design the bridge, how much it costs for people to build the bridge and the materials needed, and how much it costs to maintain and repair the bridge. So it's interesting to have cost and budget there. Anyway, but there's also stakeholders that they need to consider. I think it was supposed to be time, budget, and stakeholders. Anyway, I'm not changing that now. So stakeholders are the people who are interested in how this project will be completed. So stakeholders include, obviously, the people paying for the bridge. Now, for something like a bridge, bridges are huge and very expensive. They cost millions and millions of dollars. So bridges are usually paid for by taxpayers. So taxpayers are represented by the government. So they're the people who are in charge of that. They're stakeholders. But also stakeholders could be the people who, they might have their houses bought, whether or not they want to have their house bought, and whether or not they want to sell, they might have their land taken by the government so that the bridge can be built. So they're a stakeholder. And that's something that happened when the Sydney Harbour Bridge was built. And this still happens now, that when new roads get built, that people have to sell their homes. And it also considers other stakeholders like the environmental groups, people who protect the environment. Or it might consider motorist groups, so organisations that say this is what drivers in New South Wales want. This is the thing that we think is important. So stakeholders are the people who we need to listen to make sure that we're getting the best design. Okay. The next topic we're going to talk about is bridge materials. So the four main bridge materials that we're going to talk about today are timber, stone, steel, and concrete. And they cover the majority of bridges that have been built up until now. So the oldest material is timber, and timber is easy to join but not very durable. So when I say easy to join, it means that you can cut a piece of timber with a saw and you can join it together these days with nails, but with, there's various ways that timber can be joined. The problem with timber is it's not very durable. It means it doesn't last a long time. That timber can burn, timber can rot away, so timber can be eaten by termites. Timber just gets washed away as well. So these are all problems with timber, that timber doesn't last as long as other materials. A longer lasting material is stone. And that's not actually a natural stone, I don't think it's granite. I think that's concrete. And concrete, we'll come back to that. But stone is very durable, but so it means it doesn't burn, it doesn't get eaten by termites, it doesn't wash away nearly as fast as timber does, and it doesn't rot. But stone has a problem that it's only strong when it's being squashed. When you stretch stone, it breaks pretty easily. So what we call that is it's strong in compression, but it's weak in tension. And that's a problem with stone. And that's true of all ceramic materials. So the next material is steel. And so steel is made mostly of iron. And we could say steel, the first bridges to be made out of metal were made out of cast iron. And at the time, it was a pretty brave engineer who suggested that they were going to try and build a bridge out of cast iron. And the design that they built it out of was pretty much following a stone, very similar to a stone or timber style of construction. Though by the time the Sydney Harbour Bridge was built, steel, which replaced cast iron, was a very popular material. And steel became the main way that bridges were built until after World War II. So steel is an advanced material, but it rusts. One of its problems is the rusts. So we need to either protect it from corrosion or we have to prevent it. And it's harder to join. So we can't just join it together with nails. We have to use rivets or welds or bolts. And then the most recent material, which became popular after World War II, is reinforced concrete. So reinforced concrete involves stone and sand and a kind of glue called cement. And as well, because ceramic materials like concrete aren't very strong in tension, they're only strong in compression, we add steel. And we use the steel because it gives good strength in tension. Okay, so we're now going to talk about bridge designs, and I only have 4 here, but I'm actually going to talk about 5. So we have beams, arches, suspension bridges, and trusses. So the oldest type of bridge is a beam bridge. That's just where we just simply have a solid object that goes from one side of the river to the other, or whatever we're crossing. Could be a valley. And the earliest example is something like a log beam. That's pretty easy. You chop down a tree and you drag the log across the river. But a more modern example is the Captain Cook Bridge, which is, I think, a concrete box girder. And although that's it's obviously a much, much more complicated design, it's still at its essence just a solid object that crosses the river. The next oldest design is the arch. And the arch dates back thousands of years. The oldest arch is this is a stone arch bridge in Rome, the city of Rome, built by the Romans, and it was built in 62 BC. I think it's like Pons Fabricus or something like that, and it's in the city of Rome, and if it's not the oldest bridge, it's certainly one of the oldest bridges in the world, one of the oldest stone arch bridges in the world. A arch bridge that we're probably familiar with in Australia is the Sydney Harbour Bridge. It's not a stone arch. It's a very complicated arch. It's a steel truss arch, or arch truss, and it still applies a similar idea of the shape is mostly in compression. What's interesting is that those granite towers on either side of the bridge, they're there just purely for decoration. They don't have any functional value. They're just there for aesthetics. So the next oldest type of bridge is the suspension bridge, and these are about 600 years old. Well, the oldest suspension bridges are just rope bridges, but there are steel suspension bridges or iron suspension bridges that date back 600 years that still are existing in China. Probably the most famous bridge in the world is the Golden Gate Bridge, and it is longer than a mile, so it's 1.6 kilometers long or more than. And it, for 30 years, was the longest bridge in the world. It's in San Francisco in America. And the longest bridge in the world now is in Japan, the Akashi Kaiko Bridge, and that joins Kobe to Tokyo. So if you want a really long bridge, suspension bridges are still the best bet. And with a suspension bridge, what we have is effectively the plank, or the deck of the bridge is the term, is held up by all of those cables that hold it to the big cable on the top. And so that big cable on the top pushes all of the weight on those towers, and the bridge is held up almost like on strings. But a more advanced version of that design, we're going to come to later. First, we're going to talk about, so historically the next one is the truss. So trusses are pretty old. I think the oldest truss is like 200 years old, or maybe a bit more. Whereas trusses weren't really popular until sort of World War I, World War II. And this Warren truss is probably the simplest example of a truss. And many of you will be familiar with Tom Ugley's Bridge that joins St George and Sutherland Shire. The sort of an advanced version of the suspension bridge is a cable stay bridge, and it combines some of the principles of a beam bridge to a suspension bridge. So instead of having one big cable that runs along the length, instead it has smaller cables that join to towers. So probably the most famous cable stay bridge is the Millau Viaduct, which is in south of France near Spain. And this tower here to the right is 300 meters tall. It's taller than the Eiffel Tower, taller than Centrepoint Tower. It's a very, very, very tall bridge. And probably a well-known one in Sydney is the Anzac Bridge, which is near it joins Glebe and is near the fish markets. So I will just quickly say that cable stay bridges, they're good for medium to long bridges. So very long bridges, you want a suspension bridge, but for medium to long bridges, these are the most effective, the most efficient bridge design. So we're now going to talk about tips for your bridge. So if you're going to build a bridge as part of this unit, we want to consider certain things. So we want to consider, first of all, that we're going to load the bridge in the middle of the bridge in what's called the mid-span. So because of that, we want to consider that needs to be the strongest part of your bridge. You need to make sure that it can support all the loads. The next thing we want to consider is connections. And it doesn't matter how strong all of the parts of the bridge are if they're not joined well. And the expression about a chain is only as strong as its weakest link, this applies here, that you only need to have one bad connection for the whole bridge to fail. Another thing to consider is the bridge needs to be symmetrical. So the left and right need to be symmetrical, and each end of the bridge needs to be symmetrical. So two-way or four-way symmetry. If you don't have symmetry, the bridge will warp. It will want to twist, and that it will be more likely to fail, and it will fail with less load than if you have a symmetrical bridge. The last thing I'm going to talk about is buckling. And the concept of buckling is that if you took, say, a cardboard tube and you wanted to squash that cardboard tube, well, if you could hold that cardboard tube perfectly still, it would take a lot of strength to squash a cardboard tube. Whereas on the other hand, if you just squash it at each end and you don't hold it still in the middle, the tube will bend and when the tube bends, it doesn't need to worry about how strong it is at crushing because it's bent. It will fold in the middle, and then that will fail. So that's something that we need to consider in bridge design. And for you, how that plays out is that it's important to know that triangles, as long as you have your connection strong, a triangle won't buckle, a triangle won't warp in shape. Whereas if you have a square shape will collapse and it will form sort of a rhombus, and then eventually it will just fall onto itself. So by having if you took that square and if you put another line in between to make a square with sort of like a cut sandwich, where you had a square with a line through the middle, you're going to have a much stronger shape because it's not going to buckle. And that additional piece that we add in to prevent buckling, we call that bracing. And bracing is very important for everything from building homes to bridges. Okay, so I think now you have enough information to go on with your assignment. We know why people build bridges. We talked about what civil engineers do. We learned about the 4 main bridge materials. We learned about some bridge designs, and we learn about tips for your bridge. Now, I will suggest that most people should build a truss bridge. That should be where you should spend your time and research, because suspension bridges are very hard to actually pull off in a model. You really need to have a full-scale steel bridge to make that work. And this is normally where, if I was giving this presentation in person, where I'd ask questions, but what I'll say is feel free to, if you have any questions, that you should contact your teacher and ask them to explain anything that you don't quite understand. Okay, good luck.